Okay, in this part 2 of Unit 3 PowerPoint, we'll look more in depth with liquids, solids, and phase changes. We touched on that a little bit in the first PowerPoint, but we'll continue to be talking about intermolecular forces. And again, love little funny things. Hopefully that makes you chuckle. So just as an overview, we will talk about gases in a separate PowerPoint. This just kind of reminds you of all the different basic characteristics that you've learned before of these three in the group. So, as stated before, it's the physical properties that are caused from having weak or strong IMFs, like boiling points, vapor pressure, and then we'll get into some other ones as well today. So again, the higher the boiling point tells us that liquid must have stronger intermolecular forces between its molecules, and so we have to figure out what type of IMF is holding that substance together. So these are physical changes when we talk about phase changes. So let's talk about vapor pressure. At any temperature, some molecules of a liquid have enough energy to break free of their IMFs and become a vapor. The higher the temperature, the more molecules that have enough energy to overcome these IMFs and change to a vapor. So, as more molecules escape the liquid, the pressure they exert increases. Okay? So, the higher the temperature, the higher the vapor pressure of a liquid. Okay? Now, you have to really think about this. High vapor pressure of a liquid indicates weak IMFs. Okay, if there's a high vapor pressure of a liquid, that means it, especially at a low temperature, that means it didn't take a lot of energy for to break free of the IMF. So this is a key for vapor pressure. All right, and then we get to a pretty important graph that you'll see, and in several contexts. So notice to the right of the dotted line, we're looking at these areas that are shaded under the curve. More molecules that have a higher kinetic energy, IMFs can be broken, and these molecules can form a vapor. Okay, so really what I want to point out here is these temperatures are typically not labeled. You would be expected to realize that this lower curve actually, because if I draw a dotted line down, that curve represents a higher kinetic energy, which means a higher temperature than this taller curve that's actually in blue here. Okay? So, if there's a higher temperature, we would expect more IMFs to be broken. Now, with boiling point, and here's the official definition, okay, it's where the vapor pressure of a liquid equals atmospheric pressure. Okay, so this temperature, whatever temperature a liquid boils at, indicates how much energy is required to break all the IMFs present between the molecules. Okay, so here, and we've seen this earlier, the higher the temperature at which a liquid boils, it indicates strong IMFs. So substances, I just want to connect this to vapor pressure so you make sure you're seeing this relationship. If a substance has a high boiling point, it's going to have a low vapor pressure. Okay? Because high boiling points indicate that it has strong IMFs. Substances with strong IMFs are going to have lower vapor pressures at lower temperatures. And then here we can put this together in a graph. And you will see the term normal boiling point. And all that normal refers to is a pressure. So that's supposed to be, sea level, 1 atmosphere pressure. So if we look at this graph, remember the definition of boiling point is where vapor pressure equals atmospheric pressure. Well, if we want atmospheric pressure to be 760, which is 1 atmosphere, and we'll review some more stuff with gases later, notice that where all of these curves cross 760, and do you see those temperatures are all given? So you can definitely see waters. We know that's the boiling point of water. Those are the normal boiling points. So of these three that I've circled, what could you say about diethyl ether? Well, we would say since it has the lowest boiling point, it must have the weakest IMFs holding it together. And if you had the structure, you would be able to determine that. So, and here we go. So why, explain why diethyl ether has a lower boiling point than water. Okay, so and again, we saw it was in the, I believe the 30s, 34.6, and we know water is 100. So it has to do with IMF. So what you're expected to come up with is what type of IMF would be attracting this molecule to another molecule. Now, we see carbons and hydrogens, but if you'll remember from the previous lecture, when we see the presence of an oxygen, that is a place that makes the molecule polar. Okay? So, it's not eligible, there's not a hydrogen connected to that, so it's not eligible for hydrogen bonding. So, we would know that it's a little polar, so it can only do dipole-dipole forces between its molecules. Those are weaker attractions than the hydrogen bonding between water molecules, and that's going to take less energy to break. And I have LDFs there, and I need to update that because they're breaking dipole-dipole and LDFs. All right, viscosity. If you think about, I always think about like syrup. If it's in the refrigerator, it's cold, it's really thick. If we heat it up, we break some of the IMFs holding it together, and it would be more liquidy, not a good word, but okay, so it's just viscous is a resistance to flow. The stronger the IMFs, and then of course temperature plays a part. It also contributes to viscosity. The last three, with viscosity, surface tension, and capillary action, just kind of know the highlighted part. These aren't huge topics in AP chemistry. Why do we have a meniscus? Well, it's because the water's attracted to the glass, and then we know those little bugs can walk on water because there's a upward force due to the very strong hydrogen bonding of the water molecules. All right, let's move on to solids. Solids do have the strongest interparticle attractions and only move slightly. They just have some vibrational motion. The two main categories of solids are amorphous, which is a random particle arrangement, and crystalline, and this is what we're used to studying, this three-dimensional system of repeating points, and we call a crystal lattice. So you can see a crystalline solid, very regular range, amorphous, no repeating arrangement. Now, when we talk about crystalline solids, there are really 5 different categories of these. This might be a review, you might have learned this in your first year chemistry class. We're going to kind of go a little bit more in depth because we're going to add in our more knowledge of like IMFs, if there are IMFs present. So atomic solids, this would only be, if you'll think of nonpolar atoms, if you'll remember in my London dispersion force explanation, I talked about neon atoms. So really, the best example of what I'm talking about here is a noble gas. If you had, and think about what kind of temperatures these are going to be. If you had a noble gas that was at a low enough temperature, because obviously they're gases at room temperature, to be a solid. So we're talking like, and you'll see at the bottom, crazy low temperatures. But if a noble gas was at a low enough temperature to be a solid, it would only be held together with London dispersion forces. Because of these, they're would be extremely soft, low melting points, poor conductors, and then here we go. Neon melts at negative 248. Argon is higher at negative 189. What would cause this difference? Okay, so let's think about it. We're comparing two things that could only have LDFs present holding these atoms together. So what's the difference here between the two? Well, hopefully you'd come up with argon has many more electrons than atoms of neon. Argon has a more polarizable electron cloud. So argon would have stronger LDFs and would melt at a higher temperature. The second type of solid are molecular solids, and these really go along with the IMFs we were talking about in the first PowerPoint. So this is when we have molecules, as you see in the name, that are internally have covalent bonding. Remember, this is the substances like water, as you see at the bottom, ice, carbon dioxide, solid carbon dioxide, things that we draw Lewis structures for, and what's holding the solid together are the IMFs. Okay, so again, this was mentioned at the beginning, but just to reiterate that when these compounds melt, it's IMFs that are broken, not internal bonding. So we can look at sugar, which, C12H22O11, you might remember that from bio. Ice, dry ice, we've got our solid carbon dioxide. And then some of these substances can dissolve in water. Okay, and non-electrolyte means they don't conduct electricity. And why are they able to dissolve in water? Because they're polar molecules that can do some kind of maybe hydrogen bonding with water, or maybe a dipole-dipole. We would not really expect carbon dioxide to be very soluble in water, since it is nonpolar. Okay, so they can dissolve in water, but they stay intact as their whole molecule and have an IMF with the water. Now, ionic solids, we really studied this in Unit 2. This is anything held together with ionic bonds. This is that strong attraction between positive and negative ions. These don't mention IMFs with these. Remember, it's the ionic bonds that hold the solid together. When the ionic compounds melt, it's the ionic bonds that are broken. These are very strong bonds, so these have very high melting points. But they are brittle because the positive and negatives have to be next to each other in the crystal lattice. If they're, hit with a hammer, they will shatter because that will shift the structure, and the positives won't be next to the negatives and cause them to be brittle. They don't conduct electricity as a solid. Okay, if we melt them and they have free-moving ions, they are able to be conductors. And as we might have talked about before, if ionic solids are able to dissolve in water, they form ions, and then the solution is considered an electrolyte. This is where Coulomb's law came into play in Unit 2. All right, so remember, the more highly charged the ions, the stronger attraction in the crystal lattice, and smaller ions are closer together, so that decrease in distance causes a stronger attraction. You might be asked about not just Coulomb's law as it pertains to an ionic solid, but with ion dipole attractions, and the same rules would apply. Okay, the higher the charge of the ion would have a stronger attraction with the water molecule, or a smaller ion would have a stronger attraction to a water molecule. And covalent network, I did underline covalent because this is the key word. These are a specialized group. There is a large collection of atoms. These are going to be nonmetals. Okay, so notice nonmetals or metalloids, carbon, silicon. This is where you're going to, these have you can tell that this isn't a molecular compound because these have really strong bonds and they have really high melting points. Okay, molecular solids, since they're only held together with IMFs and not strong covalent bonds, molecular solids have low melting points. So that's how we can tell if we have a covalent compound, a covalent network, because of these strong bonds. So here's a couple of just examples. We know diamond is one of the hardest substances due to those very strong covalent bonds. And the last thing that was covered in Unit 2, we'll just briefly go over this, are metals. Okay, we call them metallic solids, but we're just talking about metals. All metals are solids at room temperature except for mercury. So it's the sea of electrons, which really means you have mobile or delocalized valence electrons that give metals their properties. Again, no IMFs. We just have these metallic bonds. If metals melt or vaporize, it's these bonds that are broken. And then the last part of this is when we go, and we've already talked about this briefly, is when we change from one phase to another. Okay, so energy is either going to be added to break IMFs between the molecules, like ice melts or water vaporizes, or if you're going the other direction, energy would be released as the phase becomes more organized. So that would be condensing and freezing. So here is more specific, and again we've attached these specific energy terms to absorbing. Endothermic is when a process absorbs energy. Exothermic is when a process releases energy, and you need to be aware of those terms and make sure you have the correct meanings with them.